The dog chased the ball because it was hungry. What does it refer to, the dog or the ball? You answer almost automatically, using the meaning of hungry and the connections among the words. But imagine a model giving one possible connection essentially 100% confidence before it has learned enough to deserve that certainty. A slightly wrong score would become a very confident wrong answer. That is our visual stake. Useful attention should be able to compare alternatives. If its scores become too extreme too early, the comparison turns into a cliff. One option wins, and nearly everything else disappears. Start without any machine learning vocabulary. For the word it, draw a line to every earlier word. A thicker line means that word currently looks more relevant. These are word-to-word connection strengths. The model converts those connection scores into weights that add to 1. Then it mixes information from the words using those weights. This compare, normalize, and mix operation is what we call attention. Attention can help carry information from dog toward it, but scaling will not solve the pronoun by itself. The model still has to learn useful representations from data. Keep that distinction in view. Now for the machinery. Each word produces a query vector. Think of a query as the features this position is looking for. For it, those features might eventually encode clues about a plausible referent. Each candidate word also produces a key vector. A key advertises features the word can offer. Query and key are learned lists of numbers, not handwritten labels like animal, object, or hungry. To score a connection, line up the query and key components, multiply each pair, and add the products. That sum is a dot product. Components that align positively push the score up. Opposing components pull it down. If the vectors have 4 components, the score adds 4 products. If they have 64, it adds 64. More terms do not automatically mean a better match, but they do change the typical numerical scale. Here are the assumptions for a clean derivation. Treat the query and key components as independent, with mean 0 and variance 1. These are an analytical model, not a claim that every trained transformer satisfies them exactly. For one component, q sub I times k sub I has mean 0. Under independence, its second moment is the product of the 2 second moments, 1 times 1, so that product has variance 1. The dot product is the sum from I equals 1 to d sub k of those products. Under the same independence assumptions, variances add. 1 plus 1 d sub k times gives variance d sub k. Standard deviation is the square root of variance, therefore the typical spread of an unscaled dot product is square root of d sub k. At width 64, the standard deviation is 8, not 1. If components are correlated, shifted, or differently scaled, this exact derivation changes. The point is narrower. With a common initialization style model, wider query and key vectors naturally produce wider raw attention logits. Those logits go into Softmax. Softmax exponentiates each score and divides by the sum, turning arbitrary real numbers into positive weights that add to 1. It also magnifies differences between large logits. A moderate set of logits keeps several choices alive. Multiply the same pattern by 8, and Softmax becomes almost one hot. The ordering did not change, only the scale changed, yet the probabilities became dramatically more extreme. The precise gradient claim is about derivatives with respect to these attention logits. For one softmax probability, the diagonal derivative is p times 1 minus p. Near 0 or 1, that derivative is tiny. Cross derivatives are minus pi times pj, which are tiny as well when the distribution is saturated. This does not mean every gradient everywhere in a transformer vanishes. It identifies one local sensitivity problem at the attention softmax. Now use a concrete width of 64. Suppose the raw logits are 16, 8 and 0. Computing softmax in code gives about 99.966%, 0.034%, and effectively 0. Square root of 64 is 8. Divide every logit by 8 and 16, 8, 0 becomes 210. Code now gives about 66.5, 24.5 and 9.0%. Scaling did not change which candidate ranks first. It changed how responsive the comparison remains. Several alternatives retain visible probability, so a small change in a logit can still produce a meaningful change in attention weight. This explains the denominator. The scaled score is q.k divided by square root of d sub k. Variance scales by the square of a constant, so dividing by square root d divides variance by d. Under our stated assumptions, the raw variance d sub k becomes d sub k divided by d sub k, which is 1. The scaled standard deviation is therefore also 1, approximately independent of vector width. Let's test the analytical story with an original fixed seed simulation. For each width, draw independent standard normal queries and keys, take thousands of dot products, and compare raw scores with scores divided by square root d. At widths 4 and 16, the raw bell-shaped clouds already widen. Their standard deviations track 2 and 4. The scaled clouds stay close to a standard deviation of 1. At widths 64 and 256, the raw spread grows to roughly 8 and 16. After scaling, both distributions again sit near width 1. The fixed seed makes this result reproducible, not cherry-picked. Sampling noise prevents every measured value from being exactly theoretical. Still, across all 4 widths, raw spread follows square root d while scaled spread remains near 1. Simulation and derivation tell the same story. Real learned vectors are not perfectly independent, zero mean or unit variance, layer normalization, initialization, correlations, training, and each attention head all shape the actual distribution. The theory is a design rationale, not a permanent law. The scaling factor controls the initial and typical magnitude of attention scores and helps avoid premature softmax saturation. It is not a magical coreference solver, and it does not guarantee that it will connect to the dog. Recap: a query meets a key, their dot product sums d sub k products. Under clear independence and unit variance assumptions, its variance is d sub k and its standard deviation is square root d sub k. Divide by that square root, the variance returns near 1, and softmax stays more responsive across widths. That is the small denominator inside scale dot product attention, and the reason it is there. Next, we can follow the values after those weights are chosen and see what attention actually moves from one word to another.